Okay, folks, so here we are on page 30 onwards, organic reactions. So it starts off with alkanes, right? So the first thing I want to tell you is all hydrocarbons, alkanes, alkenes, alkynes, okay? That's what hydrocarbons are. Hydrocarbons, if you remember, are those things that only contain carbon and hydrogen, all right? So alkanes, alkynes, and alkenes burn in excess oxygen. So the key word here is excess oxygen to produce carbon dioxide and water only. So like for example, let's say we have let's say methane gas, and then it reacts in oxygen to produce carbon dioxide and water. So you got to make sure that your equation is balanced, and the symbols for states usually is not required, but it's always a good idea to try to write it. Okay, to try to write it. So this works for all kind of hydrocarbons. Okay, it's always if you have excess oxygen. So you read the question says excess oxygen. This is what is going to happen. All right. Let's say we take something else. Let's say we take C4H8. Now C4H8 is alkene, is an alkene, and it could be butene. So plus oxygen, all right, gas, it's going to give you carbon dioxide gas, and it's going to give you water. Now water is, okay, I should put liquid, isn't it? I should put liquid because water is usually at room temperature in the form of liquid, not gas. All right, liquid. Okay, so let's balance this equation. So what I see is, you see 4 carbons here, so I'm going to put 4 carbon here. Okay, and I see 8 hydrogens here. I'm going to put 4 here, 8. That leaves me with 4 times 2, 8, 4, 4. So that leaves me with 8, 12. So I'm going to put 6 here. Is that correct? 12 oxygens on my left. I have 8 oxygens here, another 4 there, 12. All right, so balance. So in excess oxygen, we always get carbon dioxide and water only. But what happens if oxygen is not enough? Okay, in limited oxygen supply. Okay, in limited oxygen supply. So the question will tell you limited oxygen supply. You may get carbon monoxide and water. Okay, or in worst case, just carbon and water. Okay, so the question will tell you you will be prompted whether it's in excess oxygen or not. So let's say the same reaction, right? Let's say the same reaction just now, but let's say this time methane, and oxygen is insufficient. So the question will tell you oxygen is insufficient, and then your choice is either carbon monoxide, you can do this, and you can put water. Okay, so again, let's balance this equation. So if we balance this equation, 1 carbon here, 1 carbon here. Oh, sorry, I made a mistake. So this was supposed to be carbon monoxide. Sorry, carbon monoxide. Okay, so I have 2 hydrogens here, so I need to put a 2 here. Okay, that to balance. So oxygen wise, I have 2 plus 1, 3. So I'm going to put 3 over 2. Okay, 3 over 2 oxygen. So that would balance off the oxygen, yes or no? It would, right? So if I want, I can multiply this entire equation. By 2. So I will get 2 methane, okay, 2 methane gas plus 3 oxygen gas, and then I get 2 carbon monoxide, oops, there I make same mistake again, gas, and then 4 water. All right, liquid. So this is what I can do. So I can either leave it as a fraction or I can multiply it. Okay, all right, so the next thing I want to quickly explain to you is something called cracking. Now cracking is a process which is done in the petrol industry, in the petroleum industry, when you get crude oil, right? So cracking is usually done on crude oil is done on crude oil to produce smaller fractions. All right, now produce smaller fractions. I just want to tell you, crude oil is made up entirely of alkanes. So there is no alkenes, there is no alkynes, it's only alkanes. All right, they're entirely made up of alkanes. So the alkanes can be as simple as only containing one carbon, and then it can go up all the way to maybe containing 20 carbons. All right, maybe even go up to containing 40 carbons, let's say. So it can go up. So the crude oil is actually made up of all of these fractions. So cracking is a process where its use is done to produce smaller fractions, smaller parts, okay? Because very large hydrocarbons, all right, very large hydrocarbons, quite, is that how you spell quite useless. Okay, quite useless, right? So we need to make them smaller. So when you break them to smaller parts, we can use them as fuel. Okay, as fuel. So this is what cracking is all about. So during cracking, what happens is you take a large hydrocarbon, let's say we take C20 and then H42. So normally what we do is we use very high temperature and we use very high pressure, very high temperature and very high pressure. And there is no oxygen at all, So what you end up getting is you can get smaller fractions. Let's say, like, for example, you might end up getting, let's say C8H18. This is called, this is octane, right? And octane is what we normally use in our cars. So you may get an alkane. You always get an alkane, and you will get an alkene. Okay, you get an alkene. So you realize that 20 here, right? So you might get an alkene that looks like this, 24. Okay, so if you notice, if you take this number and you take this number, you should end up getting 42. And then if you take this number, 8 and 12, you should get 20. So the total number of carbons and hydrogens on the left and on the right should be the same. Okay, should be the same. So that's what cracking is all about. So cracking, the products of cracking, the products of cracking can be an alkane or an alkene, or they can be just an alkene. Let's say, like, for example, okay, you might just get C2. Okay, you might just get C10 H20. We put 2 here. Okay, so and then you might get hydrogen. So that's another possibility. So you may get an alkene, and you might just get hydrogen. So many possibilities. So when you're given a question like this, all you got to do is you got to realize that the number of carbons and hydrogens on the left and on the right must be the same. Okay, so in fact you can even choose other combinations. It does not matter. It doesn't have to be octane, it doesn't have to be dodecane or dodecene in this case, but it can be anything. The moral story is carbons and hydrogens on the left and right must be the same. Okay, now so let's move on to the next part, which would be reaction with halogens. Okay, reaction with halogens. Okay, let's look at reactions with halogens. Now, whenever we have an alkane, right, let's say you take an alkane, okay, you put an alkane into a container, right? Let's say you put methane gas and you mix it up with chlorine, let's say chlorine gas, right? And you put some UV light. Okay, UV light, all right? So what happens is there is a reaction that will start. This reaction is called can't even spell the word. Substitution. Okay, substitution reaction. So what happens in this reaction is, in this substitution reaction, what happens is every single hydrogen in methane will be substituted by the halogen. Okay, so for example, CH4 gas, and then plus, let's say, chlorine, gas, and then what will happen is you will get CH3, and then you get a chlorine, all right? So this will be gas, and then you get HCl. This is also a gas. Okay, so what happened is one of the hydrogens had been substituted. Then what happens is this guy CH3 Cl, okay, will then react with more chlorine, and then it will end up producing, let's say, CH2 and Cl2, okay, gas, and then another HCl is produced, okay, another HCl is produced. So what happened now, you realize the second hydrogen has been removed, and this can go on and on and on. Then what will happen is then from here what happens is you end up getting CH and then Cl3, and then from here you end up getting CCl4. So eventually what will happen is all, okay, so CH4 gas plus chlorine, you will end up getting CCl4 plus HCl. So if we balance this equation, 4 here, and this would be 4. All right, so gas, this would be tetrachloromethane is actually a liquid. You may not need to know this. This is what happens. So this is called substitution. So whenever alkanes undergo reactions like this, they undergo substitution where every single hydrogen gets substituted. All right, so an unimportant information here for you. So chlorine, bromine, iodine. So the intensity of the reaction, okay, becomes lower as you go down. So intensity of reaction, that means how fast the reaction happens or how intense the reaction happens. It decreases when we're going down the group, okay, decreases. So chlorine is the fastest, okay. So that brings us towards the end here. So if we take the first substituted, that means we take this guy here, we take this guy, okay, we just take this guy, this is a mono substitution. So let's say we take CH3 and Cl, all right. So we take this guy, this is called chloromethane. If we take chloromethane and then we react it with, let's say, potassium hydroxide, aqueous, okay, we mix it together, okay, and we allow it to react, we heat it up a little bit. What you'll end up getting is you end up getting an alcohol, okay, you end up getting an alcohol. So this alcohol is called methanol, okay, methanol. And then you were left with who are you left with? You're left with this guy and this guy. So what happens is you end up getting KCl, aqueous, okay. So this is you take this is another substitution reaction, all right. This is an example of another substitution reaction. So what happens here is this is also called substitution. This is also a substitution reaction. So we take the first substitution of this reaction and then react it with potassium hydroxide. We can end up getting what we call this as alcohol, all right. Now in this case, right, what I want you all to know is this: whenever we have an alkane, okay, let's say we have an alkane, right, let's say C with the halogen group, okay, let's say chlorine, right. If you remember from unit 1, I want you to remember that this reaction, this bond here is polar. So this is slightly negative, this is slightly positive. So carbon is slightly more positive and the chlorine is slightly more negative because the electrons are being pulled towards chlorine. So what happens is this carbon, okay, this carbon here, okay, it becomes it can be attacked, okay, it can be attacked by nucleophiles. Okay, it can be attacked by nucleophiles. Nucleophiles basically means lovers of the nucleus. Okay, because nucleus is usually positive, right? So it can be attacked by nucleophiles. Nucleophiles are basically lovers of the nucleus. So these lovers, right, they have one criteria. Usually the criteria is they are either negatively charged, or they have lone electron pairs. Okay, they have lone electron pairs. So examples of them are what you just saw just now: hydroxide, negative, it has lone pair. Okay, hydroxide, and then let's say chloride. They have lone pairs and they're negatively charged. Cyanide is negatively charged and it has lone pair. And then we have ammonia. Ammonia is not charged. But it has lone pair. So in that same token, we can probably also use water. Water also is another possible person here because it also has a lone pair. So these are all examples of nucleophiles. So it can come under the attack of a nucleophile. All right. So like what I just told you just now, this example here, this whole reaction that we saw here just now, right? This reaction can be called nucleophilic substitution. Okay, so this whole reaction is called nucleophilic substitution. All right, nucleophilic substitution. So in this example here, chlorine is called the leaving group, because what happens is at the end of the reaction it leaves. Okay, it's called the leaving group. At the end of the reaction it leaves. All right. So there are other reactions that we can carry out in the same token. Like for example, let's say this is the last reaction here. So let's say we have this again, chlorine. Okay, so like I told you, this is slightly negative, this is slightly positive, right? So what we can do is we can react it with we can react this with excess ammonia. Okay, we react it with excess ammonia. When you react it with excess ammonia, what happens is you end up getting this guy here. You end up getting this reaction. Now you end up getting this reaction. This becomes slightly positive, right? And then you get a chlorine here, all right? Then what happens is you can take this entity here. Which is this guy here. Okay, the same guy now. Let's draw him this way now. So this was slightly positive, right? And then you can react him with, let's say, with an alkali. All right, when you react him with an alkali, you can end up getting C, and then you get an amine, right? Methan amine. All right, and then what is left behind would be, you get water. So this is an example of the reaction that can happen. Okay, this is one, and then from here, what can happen is, okay, so this is one reaction, but from here, since you have excess ammonia, right? So this guy, okay, if you don't want to add the hydroxide, okay, so this part here is adding alkali. Okay, you add alkali. But let's say you don't want to add alkali and you're using excess ammonia. All right, if you're using excess ammonia, then what happens is the excess ammonia will react. Okay, sorry, where was I just now? Okay, so this is this one. Okay, I'm repeating back. So excess ammonia reacts. So what will happen is you will end up getting, it's the same thing. You end up getting the same thing. Sorry, you end up getting the same thing, which is amine. You end up getting amine, methane amine. But this time, this guy reacts with this, right? And you will end up getting ammonium. And remember, there was a chloride earlier, so you end up getting ammonium chloride. So I repeat. So from here, what happens is, we take chloromethane and react it with excess ammonia. We get this species here. Okay, so this is called ammonium methane, or methane ammonium. Let's say we call this methane ammonium. Okay, you get this methane ammonium chloride. You don't need to know the name. So after you get the methane ammonium chloride, what happens is you can add alkali. Okay, you add alkali and then you heat it up. You end up getting amine. You get methane, amine, and water. Or you take this guy here. You take this guy here, and then react him with the excess ammonia, because remember earlier we said excess ammonia. Then you end up getting the same thing. You get methanamine, but you also get ammonium chloride, because the chloride came from the first part here. Okay, so that would conclude the reactions of alkanes. So the next thing we'll be looking at is the reactions of alkenes.